Hello everybody, this is Dr. Christopher White and welcome back to part 2 of Rocks, part 2. So if you remember, we were just beginning to work out how we're going to classify our clastic sedimentary rocks, and we classify clastic sedimentary rocks based on the diameter of the clasts within them. So the first type of, or type should I say, of clastic sedimentary rock we'll look at are the conglomerates and breccias. Now these are rocks that are dominated by clasts which are in excess of 2 millimeters in diameter. So they're going to be dominated by gravels, cobbles and boulders. Now in terms of working out whether it's a breccia or conglomerate, it's all quite straightforward. It's all down to how angular are the clasts. If they're angular, so they have lots of sharp corners, it's a breccia. If they're rounded, so they don't have sharp corners, it's a conglomerate. So if we just go to the next slide, you can see here we have these clasts. You can see this one here got a lovely round corner there, lots of rounded corners here. Same with these clasts here, you can see the nice rounded corners there. Well, this is clear, these two are going to clearly be conglomerates. If we look at the other end of the scale though, you can see here this clast has a very angular corner. It's a 90-degree corner, and you can see that in all of these ones as well we have lots and lots of sharp angular corners, so these are going to be breccias. So is there any more information we can get out of these rocks? Well, yes, there is. The next thing we can try and look at is, well, what are the clasts? So if all the clasts are the same rock, we're going to classify the conglomerate or breccia as allocamict or allocamictic. If your conglomerate or breccia contains numerous different rock clasts in it, we're going to classify it as polymict or polymictic. So if we look at this rock here, we can quite clearly see that this conglomerate has numerous different clast types. You can see you've got these kind of dark grey clasts, you've got these kind of salt and pepper clasts, you've got these kind of brown yellow clasts here. So you have clasts that have slightly red tint to them. So we definitely have at least 4 different clast types. So this is going to be a polymict conglomerate. In contrast, if we look at this conglomerate down here, we can see that the clasts are mostly dominated by this kind of creamy yellow brown coloured rock. These are pieces of vein quartz, and we can see that most of this conglomerate are pieces of vein quartz. So this is going to be an example of an allocamict conglomerate. Same with this breccia, for instance, here. So here we have the clast in grey, and you can see that this particular breccia consists of clasts which are all the same. So this is going to be a allocamict, a allocamict breccia. Sorry, it's got a bit tongue-tied there. So once again, relatively straightforward. The final thing which we can look at is the rock clast supported or matrix supported. So what do we mean by those two? What do we mean by those two terms? Well, in a matrix supported rock, the clasts are going to be separated from each other by the matrix. Okay, so the clasts will not be in contact with each other. In contrast, in a clast, also referred to as a grain supported breccia or conglomerate, the clasts will be in direct contact with each other. Alright, so if we just have a look at this breccia here, we'll notice that the clasts themselves are separated by the matrix. The matrix is in white, so we can see, you can see the white in between this class and this class. You can see the white there between that class and that class, between this class and this class. There's the white. So the clasts aren't in contact with each other. So this is going to be a matrix supported conglomerate. Now, on the other end of the scale, we have this rock here. So this is going to be a clast supported conglomerate or breccia, because we can see the clasts are in direct contact with each other. Okay. Now, obviously not all the clasts will be touching other clasts, but the vast majority of them will be. So if your conglomerate or breccia is dominated by clasts which are touching each other, it's going to be a clast supported conglomerate or breccia. If your conglomerate or breccia contains clasts which are separated by matrix, the matrix, so they're not in contact with each other, you're going to have a matrix-supported conglomerate or breccia. So the classification of conglomerates and breccias is quite straightforward. Name the rock, and then you can simply say, right, you can say, is it a allocamict breccia or a polymict breccia? That will tell you something about, how many different rock types it will have. Just one rock type or multiple rock types. And then you can also put in extra information like, is it a class supported breccia, for instance? So if we have a look at this conglomerate here, what we clearly have is a conglomerate because we have the rounded clasts. Okay, it's clearly polymict because we have multiple different class types. And now this one's actually a little bit tricky. I would probably say it's just matrix supported because we can see there are several places where the class are separated from each other by the matrix, although there are a few locations where the class are in direct contact with each other, like right there. So this would be classified as a polymict matrix supported conglomerate. So it would be a polymict matrix supported conglomerate. So polymict, multiple different class types, matrix supported, the class are separated by the matrix, and it's clearly a conglomerate because you have the rounded clasts. So the classification of conglomerates and breccias is super straightforward. So now let's think about sandstones. Well, sandstones, as the name suggests, are made up of sand-sized clasts. Quite a big shock there. So they're classified based on the abundance of quartz, feldspar and lithic clast. So lithic clast means rock clast in your sandstone. Now, sandstones on the whole are not a hugely exciting class of sedimentary rocks because most of the time, most sandstones are dominated by quartz and feldspar, and there's typically not much else really going on. So that means if you can get any extra information into your name, if you name a sandstone, it's always helpful. So you could have things like if your sandstone has lots of iron oxide minerals in it, which stain your sandstone red, you would simply refer to it as a red sandstone. Okay, it's just that kind of little bit of basic additional information that just makes life a little bit easier for other geologists. So if we look at the sandstone classification scheme, here it is right here. Okay, so this is the standard classification scheme. We have 100% quartz up here at the point there, and this line at the bottom here represents 0% quartz. We have 0% feldspar down this axis, and 100% feldspar at that point there. And we have 0% lithic fragments on this axis and 100% lithic fragments here. So the vast majority of sandstones, are going to fall pretty much along this side because most sandstones are dominated by quartz and feldspar. So most of your sandstones will be something like an arkose or a subarkose or a quartz arenite. Now, typically, at this level, when we are classifying sandstones, we don't tend to drift off into quite this level of detail. We tend to keep it quite straightforward. We simply say, right, does this rock, which is dominated by sand-sized class, does it have less than 5% clay and silt? If it does, brilliant, you're going to classify it as a sandstone. Now, if it has more than 5% clay and silt, you're actually going to classify it as a Graywackes. Now, in terms of, let's just say for argument's sake, our sandstone does have less than 5% clay and silt, so brilliant, definitely a sandstone. Then we're simply going to worry about what's the proportion of the clasts. So if your rock contains essentially greater than 25% feldspar, so should I say if your sandstone contains greater than 25% feldspar, you're simply going to refer to it as an arkose. If it contains greater than 75% quartz, you're going to refer to it as a quartz sandstone. So, quartz sandstones will typically be quite light in their appearance because quartz obviously is typically quite a light coloured mineral, and so the rocks it will produce will also be quite light in colour. So if we go back and have a look at these sandstones here, you can kind of see they've got this kind of creamy white appearance to them. This is a good indicator that these sandstones will be quartz dominated in all likelihood. In terms of arkose sandstones, well, because they tend to have feldspar in them, they tend to have a slightly different colour. So arkose sandstones will typically have a bit of potassium feldspar in there, 25% and above. And so that will often give the sandstone a slightly pink colour. Not pink in the sense of, not pink in the kind of, pinky orange colour that rust would give it, but pink in the kind of potassium feldspar kind of pink, that kind of, salmon pink kind of colour. So Arco sandstones tend to be associated with environments which are slightly more immature. So they tend to be more immature forms of sandstone that are very often associated with areas where you're going from kind of elevated, kind of mountainous to semi-mountainous areas, and then going into a slightly flatter environment. In contrast, quartz sandstones, they tend to be more mature. You tend to get those kinds of sandstones forming in environments like deserts. Now, if your sandstone contains greater than 5% clay and silt, then it's not going to be classified as a sandstone. So if you have greater than 5% clay and silt, but less than 50% clay or silt, you are going to classify your rock as a Graywacke. Now, Graywackes are split up on a very, very coarse, using a very coarse system. You can have what's referred to as a quartz wacky, a feldspathic wacky, and a lithic wacky. And it's simply a case of, is your wacky dominated by quartz? It's a quartz wacky. Dominated by feldspar, feldspathic wacky. Dominated by pieces of rock, lithic wacky. That's it. So I should say most Graywackes are associated with marine environments. So when you're right on the edge of the continental shelf and you're just about to go into the deep abyssal plain environment, you have what's referred to as the shelf break, and then the seafloor plunges off very, very quickly. That's the continental slope. And so a lot of Graywackes are commonly associated with these kind of continental slope environments. So you're in a marine setting and the water depth is increasing quickly. Now, then we have our mudstones. So if you remember, mud is a term used for clastic rocks which contain both clay and silt-sized clasts. Okay, remember, if it's dominated by silt, it's a siltstone. Dominated by clay, it's a claystone, also sometimes referred to as a shale. But if it's a mixture of clay and silt, it's going to be a mudstone. So when we look at mudstones, because the clasts tend to be quite small, they are quite small, and you can't see them with the naked eye, it can actually be quite difficult to classify a very fine-grained clastic sedimentary rock. So what we have to do is we have to look for other features. So once again, we might note things like colour, but we also might take a second and look for other features in our sedimentary rock. And one of the most common features that we get in silt and clay-sized sedimentary rocks is a type of very, very fine layering, which we refer to as fissile, or a fissility. So if a muddy sedimentary rock is fissile, it means it has lots and lots of very, very fine layers in it. If it's non-fissile, it does not have those fine layers. So you can have a fissile siltstone or a non-fissile siltstone. The difference is, does it have the fine layers? Yes or no? Now, it was also discussed the only way to actually work out whether it's a silt-dominated rock or a clay-dominated rock is simply to start eating a bit of the rock and, as I said, just chew a tiny little flake, produce a paste which you put on the tip of your tongue, rub it against the roof of your mouth. If the paste feels kind of very silky and smooth, then your rock is going to be dominated by clay-sized clasts. If it feels a little bit coarse and gritty, it's going to be dominated by silt-sized clasts. So in terms of classifying our clay and silt-sized rocks, so here are our different varieties. So we have greater than 2/3 silt, greater than 2/3 clay, and the intermediate. Then we have fissile and non-fissile. So fissile ones, if it's a silt-dominated sediment, if it's fissile, it's a silt shale. If it's non-fissile, it's a siltstone. Clay-dominated rocks, if it's fissile, clay shale. If it's non-fissile, clay stone. And then if it's a mixture of both clay and silt, if it's fissile, it's a mud shale. If it's non-fissile, it's a mudstone. Very simple system, can't really go wrong. Okay, so what about the carbonates? Well, as discussed, carbonates are dominated by carbonate minerals, of which the most common is calcite, calcium carbonate. But you can also have rocks which are dominated by dolomite, which is calcium magnesium carbonate. Now, most carbonates are produced by the by by a buildup of organic related carbonate material. Normally, bits of shell, bits of coral, that kind of thing. So if the carbonate's being deposited due to some kind of organic process, it's going to be a biogenic carbonate. So what will happen is, over time, if you have the right environment where these animals will grow, and there'll be millions of them, and then obviously they'll be dying every day. Their shells will be falling onto the seafloor, and so over time you'll start building up big thick layers of shelly material on the on the bottom on your seabed. And then over time that layer gets buried deeper and deeper and deeper. It starts getting compressed, and then obviously the process of liquefaction takes place. And during the process of liquefaction, a couple of things can happen. Either your bits of shell will be destroyed as part of the liquefaction process, so the fossils will get lost. The calcium carbonate won't disappear, but the fossils will just get broken down. Okay, they'll just disappear. Now in that case you just have a straight limestone. However, if you're lucky and some fragments of shell or other things manage to not be destroyed as part of the liquefaction process, you will end up with a fossiliferous carbonate. So you'll have bits of shell, bits of coral, other things mixed in with your carbonate. And obviously that's quite helpful, because fossils are really, really good indicators, what the environment was, because obviously certain animals will only live in certain environments. Now, if you do happen to have fragments of material within your limestone, so let's say you have bits of shell, other carbonate particles, so you might remember from physical geology the term ooid. They're like tiny little carbonate jawbreakers almost. They look like a jawbreaker if you cut them through. Or other types of carbonate clasts, those are simply referred to as allocams. Okay, so clasts refers to clastic sedimentary rocks. Allocams refers to carbonates. So if you have a carbonate sedimentary rock, and within that carbonate rock you see you've got bits of shell and other stuff in there, well, those bits, those fragments of shell, are going to technically be classified as allocams. Now, the space between these fossils, these shell fragments for instance, is typically filled by a carbonate cement, and that's what sticks these pieces of carbonate together. Now, your carbonate cement is split into two different varieties. If you have visible coarse crystals, it's referred to as a sparry cement. Okay, so you'll have your pieces of shell, and they'll be stuck together by these larger coarse crystals of a carbonate, typically calcite, and that calcite holds the rock together. Now that's going to be a sparry cement. Now, if however your shell fragments are stuck together by a very, very fine carbonate matrix, or cement should I say, then that very fine-grained carbonate material is referred to as micrite. Now, micrite is very, very common indeed. So if we have a look at this picture here, okay, so this is Ann's Beach in Florida. Okay, now this is down by the Florida Keys, and if you've ever been to the Florida Keys, you'll know that behind the Florida Keys there is a lagoon, and the lagoon is full of this stuff, this kind of white to light yellow brown sediment. If you pick it up and you touch it, it feels kind of muddy. However, if you happen to be in the area and you have a bottle of Coke, get a pile of this sediment here and then pour the Coke on top of it. And the acid from the Coke will react with the calcium carbonate, and it will lead to a chemical reaction. You'll actually see the sediment begins to foam because of the chemical reaction. Because it's a classic acid-base chemical reaction, the kind of thing you probably did at high school. And so what we're looking at here, this very, very fine-grained carbonate material, is referred to as micrite. It's also sometimes called lime mud. And the term micrite comes from microcrystalline calcite. Okay, and so micrite is either the result of the direct precipitation of fine carbonate onto microorganisms. So in the water here, you're going to have literally billions, maybe even trillions of little algae floating around, happily photosynthesizing. And very, very small crystals of calcium carbonate are going to start to nucleate on their body. Okay, and over time, I'm sure your algae will live a full and happy life, and then eventually it will die. And obviously the organic portion of your algae will decompose, but the calcium carbonate crystals that were on the body, well, they'll just float down and settle out onto the bottom of the lagoon. You can also form micrite when you have microorganisms, so small organisms, which will actually burrow through bits of shell. So if you've ever looked at an oyster shell, you'll know that an oyster shell consists of layer after layer after layer of calcium carbonate. Now, as those layers are being added to the shell, small bits of organic material will get caught between the layers. And so what happens is once the animal itself dies, the shell will just be sitting there on the bottom of your lagoon, and algae will come along, and the algae will start to eat its way through the shell. There'll also be other organisms which can also burrow through the shell as well. And both of those organisms, the burrowing ones and the algae, they'll slowly break down the shell, and they'll be looking to try and get to the organic material caught between the layers. And in the process of destroying the shell, well, obviously the animals can't actually digest the calcium carbonate, so they just poop it out. It's a waste product, so they don't need it. They're after the organic material. And so what happens is you end up with these shells being broken down and destroyed, and you end up producing this very, very fine-grained calcium carbonate waste as a byproduct of that process. So those two sources combine together to give us the micrite, this lime mud. And micrite is a very, very common cement for carbonates. So a lot of the time when you see a carbonate rock like a limestone, there will very often be a significant micrite component to that rock. So if we have a look at this sample here, so this is a piece of limestone, and you can see, number one, no obvious fossils in it, so it's not fossiliferous, and we can see it has a very fine-grained homogeneous appearance. So this material here is going to be micrite. This is this lime mud that's been compressed and liquefied to give us a limestone. Now, sparry calcite is slightly different. Now, I must admit I am cheating here. This is actually a picture down a microscope, but you'll see this fossil, this shell. So here's the animal itself. This is the shell here. There's the hinge, which was at the back of the organism, and the animal itself used to live in this void here. Well, you can see the inside of this shell is filled up by these coarse, chunky crystals of calcite. So this is a sparry cement. Okay, and you can see some more of it here along the edge of the fossil as well. And so what you have here is this sparry cement, so you can see some more of it here, sticking together these pieces of fossil. So this is going to be a sparry cement here. You've got these nice big coarse carbonate crystals sticking the fossils together. And this would be an example of a micrite dominated rock. So no fossils in this case, or if there were fossils, they would be sitting in this very, very fine grained calcium carbonate material. So we have a micritic limestone here, a sparry limestone here, and in this case this is not a fossiliferous limestone, but this one is a fossiliferous limestone. So there are little bits of information that you can put in to describe the rock you're looking at. So if we're trying to think of carbonate particles, then there's only really two types of carbonate particle that really stand out. There's the ooids and the piezoids. So an ooid is a spherical to elliptical carbonate particle which is less than 2 millimeters in diameter. A piezoid is the same thing, just greater than 2 millimeters in diameter. So ooids consist of a nucleus, which is typically a piece of shell, or maybe some kind of silicate mineral like a piece of quartz. And what happens is the carbonate starts to nucleate around that nucleus. So you deposit layer after layer after layer of carbonate around that nucleus. And so this means over time you end up building up concentric bands of carbonate, and so you end up with something that starts to look like this. So in this case, here's the material that the ooid is growing around, and you can see we have a layer of carbonate there, another layer of carbonate here, and you can see we have several fine layers of carbonate here around the margin. And so these are ooids. They have a kind of jawbreaker-like appearance to them. Now ooids form in shallow, warm seas, and so that's a very, very good so they're very, very helpful for identifying the exact environment in which your carbonate's been deposited. So the kind of environment you should think of when thinking about ooids is very shallow, very warm, very clear water. Kind of, think of the kind of water you might get, along a beach environment in the Caribbean, for instance. That would be the perfect example of an environment in which you would form ooids in quite large quantities. The only important thing is that the environment has to be quite well protected, because ooids are quite easily damaged. And so if you're in an open environment where the wind can churn up the water, and the water churns up the sediment, well, that can be too violent and the ooids will get destroyed. So what ooids really like is to form in an environment where the water is moving but not particularly violently. So it's just being moved around by a gentle breeze, for instance. So that pretty much covers everything there. So great. So do you know what? Let's just stop the video here because we've been going for 25 minutes. So stop the presentation, get up, have a walk around, go and get a glass of water, and then come back for part 3.